Welcome to lecture 5.6, Convolution. So to motivate this topic, Laplace transforms, as we've seen, are hard to compute. We don't like doing them by hand, so we like formulas that allow us to compute a new Laplace transform from an old one. For example, here are two formulas that are very useful. If we know the Laplace transform of a function f of t, we know how to compute this Laplace transform. And it's this simple formula. And similarly, here's an even easier one. If you know the Laplace transform of f and the Laplace transform of g, then the Laplace transform of the sum, you just add those things together. So a question that's very natural to ask is there a formula for the Laplace transform of the product, f of t times g of t? That would make our lives really easy. So unfortunately, you guessed it. No, there is no such formula. However, it turns out that there is a multiplicative formula for the inverse Laplace transform. Namely, the inverse Laplace transform of big F times big G is little f star little g, where this star is called, this is not just multiplication, this is called convolution, or the convolution product, and it's given by this curious looking formula. So you multiply f of u and g of t minus u, and you integrate out the u. So it's a little bit strange to look at. Again, it takes a little while to get used to. Before I actually verify this, I want to give you some examples so you get some intuition as to what this is about. And then I'll show you how this actually comes up in modeling related to differential equations, but actually not the Laplace transforms. So this comes up in a lot of different areas in applied mathematics. Okay, so again, the convolution of two functions, formal definition, is the following. It is a function of the same variable of t, so it's different than a Laplace transform in those regards. We call it f star g, and you integrate over the whole real line of this thing here. Now you may have noticed that in the previous slide I defined it from 0 to infinity. That's because when we're in the world of Laplace transforms, the domain of our functions is 0 to infinity. So I could have made it over the whole real line, but I just didn't need to. So several properties of this, and I'm not going to verify these, I'm just going to state them, is that f star g is equal to g star f. And well, if you believe me that the Laplace transform formula works, and you'll see why shortly, one way to justify this is, well, because f times g equals g times f. So the inverse Laplace transform of fg better be the same thing as the inverse Laplace transform of gf, right? Otherwise, if that wasn't the case, then these things would be different. So these have to be the same. And similarly, we have associativity f star g star h equals f star g star h. And you can similarly come up with something like this in terms of a proof by Laplace transforms if you wanted to. Okay, so let's do some examples. T squared star t. This thing it's the integral, by definition, we integrate 0 to t of, so now we got to put f of this function f of u, so we got to put not a t squared but a u squared in here. And then we have to do not a t but a t minus u, so let's put a t minus u here. And then let's integrate du. So, okay, we can do this. This first term is going to be u cubed over 3 times t. So this is u cubed over 3 times t. And this second term is going to be, so this is u squared times u, so that's u cubed. So that's going to be u to the 4th over 4 times, I guess there's no t there. Again, I'm multiplying u squared times u and integrating. And so we have to evaluate this whole thing from 0 up to t. So if we do this, so t goes in both of these places, and we get t to the 4th over 3 minus t to the 4th over 4. Well, t cubed times t is t to the fourth, and this thing here is just t to the fourth over 12. But you did not expect that to be the convolution of these two things. Okay, let's do the second example. So what's f of t star 1? You might think it's f of t, but you would be wrong. Let's see. It is 0 times t times f of u times 1 dt. And so that is 0 to t of f of u du. So a function f of t star 1 is just the integral of that function from 0 to t. Okay. And so you may ask, is there actually a function? So this is not the identity function. You know, like an identity matrix, you multiply by anything, you get that anything back. You may ask, is there a function that acts as the identity function? So f of t star some function equals f of t, and yes, there actually is. And that is the delta function that you just learned about in the previous lecture. So let me add that here. Okay, so if you take the delta function and you take the convolution of that with some function f of t, then you get the integral from 0 to t of the delta function of u times f of t minus u du. And so this is going to pick off only one value. So we're integrating, so u is varying from 0 to t, and the only time we're going to pick off a value is when u equals t, and then we get delta of t times f of t. As we talked about in the previous lecture, that just picks off f of t. So the delta function really is like the identity function with respect to convolution. So I mentioned in the beginning of this lecture that convolution actually comes up in a lot of areas of applied mathematics and modeling. So I want to give you an example of this. And it's actually very similar to things that we did earlier in the class. And I could have actually introduced it back then in the first two sections. So this is a radioactive decay problem. So let's suppose that we have some radioactive substance like uranium, and it's decaying at some rate. So it's decaying at some rate, well, I don't want to say rate k, some rate constant k. So it's exponential decay, and k is the specific rate constant. So this is what we had in the first couple of sections. We learned how to solve this. But now we have some big bad corporation that is dumping waste and is increasing this pile. So some corporation is adding waste at some rate f of t. So now we have waste being added, and as it's added, it gets decayed, and we want to know how much waste remains at time t. You can certainly see how this is going to be a calculus problem. Okay, so to start, I want you to notice, so here's just a remark, that the amount dumped, oops, spelled that wrong, amount dumped in a time interval ti plus 1 is approximately equal to f of t times delta t. And that's easy to see. You know, think of like a Riemann sum thing. If this is like ti and this is ti plus 1, and and this is your f of t, then the actual amount dumped in this interval is obviously going to be the area under the curve, but it's approximately equal to the height times the width of this box, assuming that this is small. Okay, so we're going to use this shortly. So our goal, of course, is to find m of t, which is the mass of the waste pile. I should probably say that. Okay, so let's draw a picture similar to this. So here's what we're going to do. We're going to, so for some time t, we want to find how much waste remains, or how much waste there is from time 0 to time equals t. So it's like we were adding up like an integral, but it's more complicated because as we add things up here, they get subtracted. So let me give this actually a different label. Let me call it u. Some people call it tau, but I think that looks too much like tau. So what we're going to do is we're going to break up this interval into very small pieces. Let's call this u1, u2. Actually, let's do this instead. I'm going to call this u0, u1, u2. I don't think it matters, but I think that's might be a little more accurate. And so at some time, so at some ui minus 1 and ui, this amount of waste is dumped. This is what the company dumps in this time interval. And let me, how do I want to say this? This, I'm going to call this interval delta ui. Okay? So the amount dumped, so I'm going to just repeat what I said up here. The amount dumped in the time interval ui minus 1 ui is approximately equal to f of ui times delta. I'm just going to assume that these things are all the same width, so I don't have to keep my index here. So f of ui times delta u. Okay? So this little red amount, by the time it gets to, so it's dumped here, but once it gets dumped, it starts decaying right away. So it decays until it gets to time t. So let's write that down. So by time t, it's decayed to this amount times e to the minus, well, let's just write this out. It's decayed to f of ui. So this is how much, this is the mass of that little blob that I drew, u, times e to the minus k times the amount of time it has to decay, which is t minus ui. Okay? T minus ui. So this is the amount that it decays to after time t. So the total amount left at time t, so now we have to, instead of this, we have to add up these blobs on every single time interval. So we have to do the same thing. So we're not adding up the masses of these things, we're adding up the masses, this is the mass, times this exponential, which takes care of the decay. So the total amount left at time t, I think we called it m of t, it's approximately equal to the sum of I equals 1 to n of f of ui times e to the minus k t minus ui times delta u. So you probably know what's coming next, is instead of taking a finite sum, we let delta u go to 0. So let's do that. Let delta u go to 0, and this thing becomes an integral. M of t becomes the integral from 0 to t of f of u times e to the minus k t minus u times du. Okay? And now notice that that is actually just a convolution. This is f of t star e to the minus k t. Now what I want you to notice here is f of t represents how much was added by the big bad company, and this represents the intrinsic decay rate of whatever the material is. In this case, I think it was a uranium. Okay, so this works in general. If you have something that is being added to at some rate and decays at some other rate, then this convolution gives us a formula for how much there is at time t. So some modifications of this, I don't have much room left, but let me just say a few examples. So another example of this is, suppose that we were to, instead of dumping uranium, suppose we were to just dump garbage. So then that doesn't decay, so the decay rate is k equals 0. So suppose we were to dump garbage. So that means that the rate k equals 0. Then, in that case, m of t is just f of t, convolution of that with 1, which, recall, was just the integral from 0 to t of f of t. And that's what we expect. We're just adding up the amount of garbage so we're dumping garbage at this rate from 0 to t, and the amount of garbage at time t is just the integral of that. Okay, so what about if instead of an intrinsic decay rate, suppose you have an intrinsic growth rate? I really am running out of room here. Let me make a little more space. I mean, I can really just say this, but let me just write down a note or two. So suppose you have an investment. So you have an investment and you are adding to your portfolio at some rate, f of t, and your portfolio is growing at some intrinsic growth rate, then this is a way to figure out how much money you have after some number of years. So another example, when k equals, when k is greater than 0 is finance. So you have, so maybe you're adding to your portfolio. I think that's all I'm going to write. I think it should be clear that this is the rate that you're adding, and this is going to grow at some rate. Okay, so now that we've taken a short tour with convolutions, let's go back and revisit our original motivation for introducing these things, namely that the inverse Laplace transform is multiplicative in the following sense. L inverse of f times g is little f is the convolution of little f and little g. So let's prove this statement. It's actually not that bad, though it does involve a little bit of vector calculus, or Calc 3. And this, I think, is probably the only real application of vector calculus in this course. Most of the course is just derivatives and integrals, and in theory it could have come right after Calc 2. But for this we definitely need double integrals, and we will be changing the order of integration and changing variables. So let's write out what this thing is. So this, just by the definition, is each of these is an integral. I'm going to write this as f. Instead of using t, I'm going to use u. And you'll see why shortly. Well, one answer is that I actually need two different dummy variables. So I'm going to call this one g of v e to the minus sv dv. But also I'm going to make a substitution and do a change of variables, and I'm going to sub t back in. So I actually want these two variables to be something that are not t. So this thing here is, let's get my pen back. This is a double integral of f of u, g of v, and now we have e to the minus s, u plus v, du dv. So what I want to do is I actually want to, so this thing looks similar to a Laplace transform. I know there's an extra integral in here, but we have some function times e to the minus s times something else. What we're going to do is we're going to look at that, s plus u, and I want to call that t. So in other words, we're going to change variables. So let's write that out. Let's change variables. I want to let t be equal to u plus v, and then I want to eliminate either u or v. Doesn't really matter which, so I'm going to let u be equal to u. So instead of using u and v, I'm going to use t and u, and this is going to get us to this convolution formula by eliminating v. Okay, so this integral here, I don't know what I want to call it. Let's put a star up here. This integral. Under this change of variables, let's try to figure out what it becomes. So it's going to be a double integral. And the limits are the hardest part. Okay. So what's inside of it? It's going to be f of u. So this is not changing. G of v. Now notice, with v I have u. So u is the same, but v is now t minus u. So g of v now becomes g of t minus u. And now I have e to the minus st as desired. And now I have to be careful. I have du, well, that's not right. I have du dv. This here, remember that this is our dA. And when we change variables, we actually have to be careful because remember what we have to do? So this is one of the details from vector calc. So this is du dv is something mysterious times du dt. So we have to do so we can't just take du dv and put in du dt. We have to put the Jacobian. Remember that? So this is the Jacobian. It's the partial of u with respect to v, and the partial, or it's this thing. And let's refresh our memory what this is. This is the Jacobian. Sometimes it's called J. I'm not sure what they would call it in your class because the notation sometimes can change. All it is it's just a 2x2 matrix of partial derivatives. It's a determinant, that is. So it's u with respect to u, u with respect to t, v with respect to u, and v with respect to t. So you probably learned this in vector calculus. You probably didn't know it was called a determinant because you probably didn't see 2x2 matrices until this class. You probably learned it was this cross product thing. So what is this thing? Let's look here. The derivative of u with respect to u is 1. The derivative of u with respect to t, well that's 0 because there's no t up here. The derivative of v with respect to u is -1, dv du. That's -1. And then the derivative of, what's the other one? The derivative of v with respect to t, that's just 1. So, okay, so this determinant is equal to 1. All that work just to say that we needed a scaling factor of 1. If you had forgotten that, you still would have gotten the right answer. So now we can put du dt. And if you This thing should go in here, but it's 1, so we don't need it. Okay, so now the hardest part is probably coming up with the limits of integration. So now that we've changed variables, what are we doing for, what are these limits? So let's draw a picture. It's almost impossible to do these things without drawing pictures. So this is u, and this is v. And so we want to integrate over the region where u varies from 0 to infinity and v varies from 0 to infinity, meaning that is this first quadrant. So we want to integrate over this quadrant, this region. I'm a little hesitant to shade this in because I think that just may make the screen a little messy. So normally what we do is we integrate with respect to u, with respect to v, we integrate with respect to u, that means we hold v constant. So that means that we are holding, that we are integrating along these lines, and then we're integrating along these lines. So now what we want to do is we're going to integrate along with respect to u, so we're going to vary u, and we're going to hold t constant. So what is t? T is u plus v. So when t is constant, that corresponds to a line like that, this. So these are the lines of the level curves of constant t. So when we're integrating from over this region, we have to start from u equals 0. That's going to be along this axis. So when we start here, this is when u equals 0. So that's when we are entering this region, this quadrant. And then we are moving along in the direction of constant t's, or along the t's, and then we are exiting the region when we are right here. So we're starting at u equals 0. And so what happens here? So these points are when v equals 0. So what does that mean? So when v equals 0, well, let's go back over here. When v equals 0, that means u equals t. So that's the same thing as saying u equals t. And again, that's because t equals u plus v. So we're integrating from u equals 0 to u equals t. Kind of strange, I know. So that's in the, with respect to u, so across the t directions, and then we are integrating along these lines from t equals 0, that's here, all the way up to infinity. So from t equals 0, so from t equals 0 to infinity. So we integrate from 0 to infinity. Okay, so we're almost done. So now we have this integral. I guess it looks a little closer to this formula, and we see an exponential here. But notice that this exponential does not, well, let's put a parenthesis here. So this is that first integral, but this exponential does not have a u in it. So I can pull that thing outside of the integral, that first integral anyways. In other words, I can write this as the integral from 0 to infinity of e to the minus st times the integral from 0 to t of f of u g of t minus u du dt. Okay, now what have we just done? So what is this? This thing in here is this is the Laplace transform. No, not the Laplace transform. This is the convolution of f of t and g of t. And this thing, this big integral, we're multiplying this convolution times e to the minus st and integrating it from 0 to infinity, that's the Laplace transform. So this thing here, what we have just gotten, is that this is the Laplace transform of f of t, the convolution of f of t, and g of t. And now, why is that verify what we wanted? Well, that's exactly what we wanted, because that is equal to f of, we started with f of s, g of s, and this is an alternative way to describe this formula, because we can just take the inverse Laplace transform of both of these sides, and we get, take L inverse of this, and we get f of t star g of t, and L inverse of this is what we get. So notice that this equation is equivalent to this equation up here, and that is the proof.